Okay, let's talk about a few more examples of impulse forcing. So let's do an undamped oscillator this time. So here we're going to have d squared y over dt squared plus 4y is equal to delta 0 of t. And we are going to have y at 0 being equal to 0. And y prime at 0 is going to be 0, kind of. Okay, we're hitting this force at time 0, and at time 0 we're going to have a jump in the velocity. So the left hand limit of the velocity is going to be 0. All right, so we are going to hit this oscillator at time 0. So we are going to take the Laplace transform. On the left hand side we have s squared, Laplace transform of y, minus s times y at 0, minus y prime at 0, plus 4 times the Laplace transform of y, equals the Laplace transform of delta 0, which is e to the minus s times 0. So when the dust clears here, we have s squared plus 4 Laplace transforms of y equals 1. E to the minus s times 0 is 1. So that means the Laplace transform of y is 1 over s squared plus 4. And so y of t, which is 1/2, 2 times divided by s squared plus 4. So that means that the inverse Laplace transform now is going to be y of t is 1/2 sine of 2t. Here the omega is 2. All right, so that is the motion that results. We get a periodic motion that doesn't damp forever. All right, we hit this at time 0, and there's what y is. Now the velocity, the derivative of time, is going to be cosine of 2t. And you see now the velocity at time 0 is 1, but we had a velocity of 0 here. Well, what we're really doing is immediately after, right? This velocity is only for time greater than 0. At time 0, we have 0 velocity. Then we're hit, and then immediately thereafter, we have a velocity of 1, something very close to 1. So that's kind of a strange outcome that we get with these instantaneous impulses. Okay. So let's do another one, but instead of just hitting it once, let's hit it lots of times. So let's try this again. Let's start with the same oscillator, d squared y over dt is plus y is not just going to be d0, but we're going to have d of n times a of t, and we're going to do this many times. We're going to start at n equals 0, and we're going to do this forever. So every a seconds, we drive the system. With a short impulse, right? Just an instantaneous impulse. And we're going to start from rest. All right. So what's going to happen here? Well, this is kind of interesting. The left-hand side is similar to last time. I have s squared plus 1 times the Laplace transform of y. On the right-hand side, we take the Laplace transform of each of these impulses. The first one is e to the minus s times 0 times a. The second one is e to the minus s times a times 1. The third one is e to the minus s times a times 2, and so on and so forth. So this is equal to 1 plus e to the minus s a times 1 plus e to the minus s a2 plus etc. And let's isolate the Laplace transform of y. So we get 1 over s squared plus 1. And then we get s squared plus 1, the denominator of all of these terms here. And now, unrigorously, we're going to take the reverse Laplace transform. So y is going to equal, well, 1 over s squared plus 1. We just did that one. Right? Well, not quite, but that's going to be sine of t. This one looks like sine of t, but with a time shift, and that it is because this is the force that comes a seconds later. So this is going to be u a of t times sine t minus a. And this next one is u2a of t sine t minus a, etc., etc. So what we're going to get now is these signs, but we're delaying the additional ones that we're adding. Oh, and this shouldn't be t minus a here. This should be t minus 2a. So think of this as something like the motion you get with pushing a swing, right? If the a's line up with the sine function, you'll get an increasingly large response out of this. If the a's have nothing to do with the period of the sine function, and the period of the sine function is 2 pi, then you kind of get a very chaotic response eventually. If you think about pushing a swing, you're always pushing the swing when the swinger is at the apex going backwards. But if instead you were pushing a swing and you decided, I'm going to push this person every second, no matter what, and it didn't matter where they were in the swing journey. Sometimes you would be pushing them at the top, sometimes you'd be pushing them at the bottom, sometimes you'd be pushing them when they're going forward, sometimes you'd be pushing them when they're going backwards, and you'd have a very chaotic swing ride. And that's what that function y would be if the a is not involved with the sine function, period, right? If a was equal to 2 pi here, we would have a sine function. It goes all the way through its period, and then we'd get another sine function. So the motion would be sine t for the first a seconds, first 2 pi seconds. Then it would be 2 sine t for the next 2 pi seconds. Then it would be 3 sine t for the next 2 pi seconds. We get a progressively larger response out of this, right? So that the picture that would get out of that would be as follows. Let me just draw this, right? So we'd have first we'd start with the sine function for the first period, and then we'd have sine 2t, so we got twice as large. Then we'd have 3 sine t, so we'd have a response that kind of looks like this, right? That would be if we deliver our impulse in line with the period of the sine function. But if we're not doing the impulse at the right time, then you're going to get something very chaotic over time. It's not going to look pretty. All right, so that was an example of impulse forcing.